Great. This lecture will be recorded, just so you're aware. I'd like to start by acknowledging that this event is hosted on traditional lands across Australia. I'm in Canberra, and Canberra is Ngunnawal country. The Ngunnawal are the Indigenous people of this region and the first inhabitants. I'd ask you to join me in acknowledging and in celebrating the first Australians on traditional lands that we meet across this land and airwaves, and pay our respects to elders past and present. The talk today will be split into two halves, roughly reflecting this year's Nobel Prize, which, as we all know now, was awarded half to Sir Roger Penrose for his theoretical breakthrough in the field of black holes, and the other half shared jointly by the observational astrophysicists Andrea Getz and Reinhard Genzel. The talk today will be first presented by Susan Scott from the ANU and OzGrav, and will detail the work and background of Roger Penrose. Susan Scott is a professor of theoretical physics here at the Australian National University and is part of the Centre of Excellence for Gravitational Wave Discovery, OzGrav. She is a general relativity theorist and has been working in this area for many years. Indeed, she spent 4 years on a Rhodes Fellowship in Oxford working with Sir Roger Penrose, so we're looking forward to a few personal anecdotes. Susan is a fellow of several learned institutions, including the Australian Academy of Science and the Australian Institute of Physics. The second part of the talk will then be presented by David Blair from the University of Western Australia and also from OzGrav. David is a gravitational wave physicist who has spent more than 4 decades developing methods for detection of gravitational waves. He's a founding member of OzGrav, and his belief and hard work in the area is legendary in Australia and date back decades. He has a strong interest in outreach and education, and David will present the second half of today's lecture, which will include a review of the seminal contributions by Australian radio astronomers, and then outline the discoveries made by Reinhard Genzel and Andrea Getz. Some quick housekeeping. We encourage you to use the Q&A button below to ask questions. You don't have to wait till the end before you type in your questions. If a question occurs to you, please type it in. I will be reading out the questions and then I'll leave it up to David and Susan to decide who to answer them. If you want to switch your screen to side-by-side speaker, you'll probably get the best view with the slides in the middle and the speaker on the outside. And a reminder that this talk is being recorded. So without further ado, let me hand over to Susan, who will start today's presentation. Thank you.
Yes, so thank you very much for that introduction, Jodie, and good morning everybody who's in Australia, and greetings to those who are elsewhere. As Jodie said, I'm based in the ANU Centre for Gravitational Astrophysics, and I'm a chief investigator with the ARC Centre of Excellence for Gravitational Wave Discovery, which is OzGrav. So my talk is going to be about the half of the Nobel Prize, which went to Roger Penrose. And first, let me say that I was absolutely delighted to have this year's Nobel Prize go to black holes, because personally, I adore black holes. So this was very exciting to see this finally recognized. And in particular, for Roger, who's going to be 90 in August next year, for him to receive this enormous recognition of what is an absolutely spectacular piece of work. As Jodie said, I worked for 4 years on a postdoc on a Rhodes Fellowship in Oxford with Roger, and I had the great fortune to get to know Roger very well during those years, and also to be at very close range to his incredible genius, which I will talk a little bit more about as I go along. Just as a personal note of things that were happening in Oxford at that time, as a research group, we were discussing singularity theory. We were discussing concepts of quasi-local mass, which is Roger's new approach to defining energy, momentum, and angular momentum in general relativity. We were thinking about gravitational entropy in relation to the birth of the universe. We were, of course, talking about twistor theory as a basis for physics from which the fabric of space-time should emerge. And surprisingly, we're also talking a lot about Turing machines, because one of the senior postdocs in the group, Andrew Hodges, had finished writing a book a couple of years earlier called Alan Turing, The Enigma, which was about Alan Turing and his time at Bletchley Park breaking the code of the Enigma. And this was all very exciting at the time. The book was being translated into many, many languages, and it had been made into a play which the whole group went to see in London's West End a few months after I arrived. So there was a lot going on in that period. And also that first year I was there, there was a very big international workshop at the Institute for Theoretical Physics in Santa Barbara in California. And from our group, Roger, myself, and another postdoc, Lionel Mason, went for that 3-month workshop and shared a house during that period. And on one of the weekends during those 3 months, the three of us plus the person on the left, who's called Ted Newman, who's another well-known relativist who I'll mention briefly later, actually went to Death Valley and climbed Wild Rose Peak. And that is a picture of the two of them at the top of the mountain. And just a comment from that is that I observed that Roger was extremely agile, even at that time. And he reminded me of what Australians will know as a yellow-footed rock wallaby, in that he was jumping between rocks in a very kind of agile way. So that's a little bit of the backstory. But of course, the whole story about black holes really begins with Albert Einstein. So we'll start there. And arguably, of course, our most famous theoretical physicist. And in 1905 was responsible for introducing the photoelectric effect, Brownian motion, special relativity, and the equivalence of mass and energy through the formula E equals mc squared. But to my mind, his greatest contribution came 10 years later in 1915 with the general theory of relativity. And I sometimes wonder if Einstein had not discovered each of these particular effects and phenomena, how long it would have taken for somebody else to do so. And I do think it would have taken really quite a long time for general relativity to have been devised by someone else. So without going into any great detail, the theory appeared in 1915, and it was a unified description of gravity as a geometric property of space and time, which is what we call space-time. And Einstein presented his field equation, which I've got written there, and I won't talk about it in detail, but basically it's a beautiful coming together symbiotic relationship between geometry on the left-hand side of the equation and mass and energy on the right-hand side. So this is the equation, and the idea is that matter warps space-time. And here is a picture of our Earth and its moon. And Earth is 81 times more massive than the moon. And so we can see, according to this picture, it's denting or curving space-time much more. And it's this curvature that we perceive as gravity. And I had to put in here a famous quote by John Wheeler, which you've probably all heard, which is, matter tells space-time how to curve, and space-time tells matter how to move. So the story of black holes themselves really begins shortly after that with Karl Schwarzschild. Now, Karl was a German astrophysicist, and 1915 was, of course, during the First World War. And surprisingly, Karl enlisted in the German army at the age of 40. And he served on the Western Front and later was stationed on the Eastern Front. And it was while he was on the Eastern Front that he set himself the following problem. He was a very practical person, being an astrophysicist, so he wanted to find the gravitational field corresponding to, coming from the Einstein field equation, corresponding to the area outside of a spherically symmetric star. Now, he chose spherically symmetric because the Einstein field equation is incredibly difficult to solve, and you need to have everything going for you to have any chance at all of solving it. And so spherical symmetry helps a lot. And Karl wanted to know what the field would be like outside of a star. So he set himself the task of finding that field outside of a spherically symmetric, non-rotating star. So Karl would have been occupied fighting the enemy during the day, and probably as a minor officer, a lieutenant, by night, he would have been in his small tent, beavering away, trying to do this by lantern light. And he did. He found the solution. And somehow he got that couriered, possibly by donkey or something, back to Europe, and Einstein presented that to the Prussian Academy. And this was several months after the theory was presented. And Karl still wasn't satisfied. He then set himself the problem of finding the solution for the interior part of the star. And he was successful in doing that. And that was also couriered back to Germany. And Einstein also presented that on his behalf. And sadly, a few months later, Karl actually died. And he didn't die of battle wounds. He died of an illness he contracted on the front. So fortunately, he did this rather important work prior to all that happening. And he possibly would have gone on to do many other great things, but didn't have the opportunity. Shortly after I arrived in Canberra from Oxford, I had the opportunity to meet Karl's niece, who was living on a farm not too far out of Canberra. So that's another sort of connection to this story. Now, Karl had noticed that this is his metric here, and it's presented in spherical polar coordinates, so a time coordinate, a radial coordinate, and two angular coordinates. It's diagonal, and we can see, just looking at it, that there's a problem with the metric components of 1 minus 2m on r equals 0 when the radius equals 2m. Now, just pointing out that I'm using geometric units here to simplify things, so don't worry about if some constants are missing. And the other metric component becomes infinite there. Now, Karl would have seen this, and he did, but he wasn't worried about it because at the time he was doing this, there were not sufficiently dense stellar objects out there that he was aware about where he would have had to worry about the radius of the star being anywhere near close to r equals 2m. So he was quite satisfied with this. And another small note is that also when I moved to physics at ANU, the person in the office next to me called Hans Buchdahl was a well-known relativist. And in the 80s, he actually found an interior solution for the Schwarzschild metric, which was a lot more physical than the one that Karl had found. So now we're moving on, 20 years or more, and we're going to think about the work done by Oppenheimer and his student Snyder, because by this stage there was significant interest in stellar collapse, the collapse of stars. So basically the sun and other stars are held in balance between their gravitational self-attraction and the pressure of thermonuclear reactions. After all their fuel is spent, they explode as, let's say, a supernova, and then they collapse. And what we now know is that if they end up at about less than 1.4 solar masses, they are a white dwarf. If they end up somewhere in the range between about 1.4 and 2 point something solar masses, they're a neutron star. And somewhere over 2 solar masses, they're black holes. This wasn't known to Oppenheimer and Snyder at the time. So they'd looked at Schwarzschild's solution and seen this issue with r equals 2m. So they set themselves the problem of solving the spherically symmetric situation for gravitational collapse in the case of dust matter, which is, in general relativity, that's a pressureless perfect fluid. And they solved the equation and found their solution and realized that they could have the surface of the star contracting all the way in through r equals 2m and beyond towards the center of the star. And obviously this was surprising But they thought at the time there must be some sort of physical effect that they didn't yet know about, which would prevent this collapse from fully happening. And the issue is, when you look at the time and radial coordinates in Schwarzschild's metric, then you can see that there are these curves, which is like an infalling radial observer, in this case a light-like one, so it could be a photon. But what happens in these coordinates is that as they approach the surface r equals 2m, their time coordinate goes infinite. So it was known that this was not a good representation, because Oppenheimer and Snyder had seen that the surface of the star will get to r equals 2m in finite proper time, which is the time that the observer experiences themselves. And so some other new way of representing the Schwarzschild metric was necessary. And this might not seem like a big deal, but it actually took 45 years from 1915 to about 1960 to fully solve the problem of what was going on at the radius r equals 2m. So it was very problematic. It was debated. There were a lot of different thoughts about it going on, but it was finally understood in stages. And these two people, Arthur Eddington and David Finkelstein, played an important part in that Finkelstein devised a new time coordinate, which you can see in this diagram down the bottom. And basically, infalling radial observers will now get to this surface r equals 2m in finite time. So that was good, because we now had a picture of how observers can move through that surface. But the full picture wasn't obtained until about 1960. And this is the full picture using a Penrose diagram named after Roger Penrose. And a Penrose diagram basically brings the whole diagram of space-time into a finite distance. It brings the infinities into a finite distance. And the idea was that we can study the radiative properties of space-time if we bring in those infinities to a place where we can actually look at them. And here, the Schwarzschild metric is represented as a Penrose diagram. So you've got outside the black hole in this region, you've got r equals 2m here, and this is the event horizon. So that if any observer gets to that event horizon, they have no option but to proceed into this upper region of the black hole. And that black hole, the jagged part at the top represents what we call the singularity. And that is a place of infinite curvature in the space-time, which in this case is caused by infinite density of the star having basically collapsed to a point. So you can see on that blue curve there that the observer is passing from the outside region of the black hole through the one-way membrane of the event horizon and getting down into the singularity. So this final part of the picture was done kind of independently by Martin Kruskal, an American relativist who I met soon after I arrived in Canberra, and also George Zekaros, who was the father of my PhD supervisor, Peter Zekaros. And George, although was an immigrant from Hungary during the Second World War, actually was well and truly in Australia when he did this piece of work. So that's another Australian connection. Yes. And so basically this was the black hole solution. It was understood by this stage, let's say late 50s. And the idea is that we had the event horizon surrounding the singularity at the center, and nothing which gets inside this event horizon can escape. So that's the black hole solution. Now, 3 years after that, in about 63, a New Zealander, Roy Kerr, found the solution for a rotating black hole. And this was a huge deal because obviously we expect things out in the universe to be rotating and spinning. And so the Schwarzschild solution wasn't particularly physical from that point of view. And what was a very, very difficult problem Roy solved and actually obtained the rotating black hole solution. And for this, in 2016, he won the Crawford Prize from the Royal Swedish Academy of Sciences. And Roy is very well known for that solution. And this is a little bit of a shameless plug for our book about the Kerr space-time, which was with Matt Visser and David Wiltshire. So this is the thinking of singularities about this time in the 60s. Both the Schwarzschild solution and Kerr solution have singularities. That's places in space-time with infinite curvature, caused by infinite density in these cases. And up to this time, most general relativity theorists, including Einstein himself, believed that black holes and singularities would not exist in nature. And the thinking was that the Schwarzschild and Kerr solutions had these singularities simply due to the very high degree of symmetry assumed. Because everybody knows, looking out into the universe, that nothing is, for instance, spherically symmetric. You know, our stars have flares and mountains and crags, and you know, when we look out there, we don't see anything that is exactly spherically symmetric. So they thought that had to be the problem, and that these singularities would not occur in more general solutions. So Roy, meanwhile, was presenting his solution to an audience made up mostly of astronomers at the Texas meeting in 1963. And this presentation, reputedly, according to Roy, didn't go very well. The highly mathematical content of presenting the solution wasn't terribly accessible for them, but also the astronomers at the time thought this so-called singularity was absolutely absurd, some kind of failure of the general relativity theory, and there would be some kind of mechanism from preventing gravitational collapse from going that far as to form a singularity. So it did not go down well. The whole concept wasn't well regarded by the astronomical community. But then came Roger Penrose, and from the late 1950s, there were some very new mathematics in general relativity. There was differential geometry and differential topology, and these changed the face of relativity in such a way that modern relativists looking back at textbooks in the 30s and 40s would find them very difficult to read. And Roger was emerging in the late 50s. He was a mathematician, and he was very attracted and inspired by the techniques of differential topology. And furthermore, Roger was looking at everything that was going on around him, and you know, there was slowly the advent of the quasar in the early 60s. And Roger felt that there were these very extremely dense, compact objects out there, and that it did seem likely, in fact, that black holes might exist. And so he set about using these sophisticated techniques from differential topology and argued that any object with an event horizon, regardless of its shape, will contain what he called a trapped surface. And so a trapped surface, you know, like a closed surface, if you put little light bulbs everywhere, then all the light shining from those would all shine inwards towards the center of that surface. For instance, if it's a sphere, to the center of that sphere. And the theorem shows that you can have this arbitrary symmetry of these surfaces, and you will still get this singularity at the center. So the implication is that anything inside a black hole has only one possible future, and that's falling further and further towards the center. The collapse process can't halt, and it keeps on going until you reach a catastrophe, and that is the singularity. So to summarize his results, his singularity theorem showed that if you assume general relativity and also sufficiently massive objects undergoing gravitational collapse, which we already knew at that time was happening, then you will get black holes. And this will be irrespective of the shape or symmetry of the object which is collapsing. And furthermore, and even more powerfully, it's for a very wide range of possible matter contents of the stellar object. So it wasn't a very simplified, specific form of matter like dust or anything. It was very, very wide conditions on the matter content. So this was an extraordinary result, and it's one of the few things that Einstein didn't predict. He'd predicted gravitational waves, gravitational lensing, perihelion precession, just about everything else. But he had no idea of this, and he didn't quite live to see it. And I think he would not have been very happy because he didn't like black holes or singularities. But I think he would have eventually come around and embraced it in the fullness of time. But the upshot of all this is it changed everything, because general relativity had now predicted that there should be a vast, pervasive population of black holes throughout the universe, and they should exist. And together with Stephen Hawking, who was a regular visit to our group in Oxford in the years that I was there, they established a number of other singularity theorems and basically showed that every black hole contains a singularity and every expanding universe began in a Big Bang singularity. And to my mind, these singularity theorems, and I think to a lot of other people who work in the field, these have been the biggest advance in general relativity theory since Einstein presented the theory in 1915. And just to complete that story, also in the 60s, a little later, it was shown by other people, other relativists, that there can be only 4 types of black holes, basically uncharged and charged, and rotating and non-rotating. And the one that we believe is the physical one out there in the universe is Roy Kerr's black hole, the rotating non-charged black hole. And I often wonder if Roy goes out and looks up in the sky and thinks about all his black holes up there spinning around. It must be quite a unique feeling. The other amazing thing about this story is that it had gone full circle. People not wanting to believe in singularities because they were spherically symmetric and had this high degree of symmetry. And here we are, the only types of black holes you can have are incredibly highly symmetric. So this was a very interesting conclusion to that. And so by the late 1960s, basically the main theory about black holes as we know it today was wrapped up by the general relativity theory community. And yet there still hadn't been a serious candidate. And the first serious strong candidate for a black hole came in 1972, which was Cygnus X1, and it was in an X-ray binary system. And of course, since then, we've found many, many other candidates. And what I think is a beautiful end to that story is that with a detection of gravitational waves on the 14th of September 2015, we detected that signal, that gravitational wave signal, from 2 solar mass black holes, 36 and 29 times the mass of the sun, colliding to form a 62 solar mass black hole. So this was an absolutely beautiful story that, 100 years since Einstein devised his theory, we had 2 of the greatest predictions of it coming together in one moment, gravitational waves and black holes. So Roger played an absolutely critical and major and time-changing role in the history of black holes. He actually changed the face of the way the whole community was viewing the situation with black holes. But, he did so many other things. I'm not going to talk about them. Lots of impossible diagrams like the Penrose triangle, Penrose diagrams on the right, which we've talked about a bit, the possible mining of energy from black holes, twistors, which I also mentioned, and another impossible diagram on the lower left, the idea of cyclic cosmology, so the universe being reborn over and over again, and also these non-periodic tilings of the plane, which were very, very big also in the time I was in Oxford. And soon after I got there, Roger went away for a few weeks for work and asked me to check in on his house. And I noticed while I was doing that, that he was building a non-periodic tiling on the floor of his bathroom. So that work was definitely in progress at that time. And just to finish, here's a final picture of Roger. I would say, personally, he's the most ingenious scientist I've ever seen at close range and worked with. He has a unique way of thinking about things that I've never seen with anyone else. Very geometric, and Roger can think in 4 dimensions and does. So he's a very remarkable character, and congratulations, Roger, so well deserved. Thank you.
Thank you, Susan. Lovely to hear those little personal anecdotes. It really brings it home that how remarkable these discoveries are.
I'm going to go on now mainly to talk about the other 2 Nobel Prize winners. Here are all 3 of them. You've already seen Roger, and there's Reinhard Genzel and Andrea Ghez for the discovery of supermassive compact object at the center of a galaxy. This Nobel Prize is the 5th Nobel Prize in sort of astrophysics and cosmology. And I suspect that we may see many more in this area in the future. And here you see the 3 people that we're talking about. I'm talking about the 2 on the right. But before I do, I want to just say a little bit about Roger Penrose, because he visited the University of Western Australia in 2008. I just have a slight problem here, which is I can't, I'm blocking my own screen, so I can't read what I've got there. But I was just looking up some review papers on singularities, and found this comment that the impact of Penrose's work was ample, profound, and straight away. So immediately the general relativity community was impacted by his work, and even though the Nobel Prize took such a long time coming. On the internet to see if I could find out actually when he came, and I found this news article from a university news magazine that said the pattern of floor tiles, an intriguing street sculpture, contributions to general relativity may seem unrelated, but all come from the brilliant mind of Sir Roger Penrose, who actually came partly because we had just installed a set of his tiles in our Cosmology Gallery, which I'll show you a picture of in a moment. But he gave a public lecture on the Big Bang, and he did a fabulous session called Big Questions for Bright Minds for school children. So, and in all of this, he charmed everybody. But I couldn't find the happy snaps that we took. We're in front of his impossible triangle, but there's an impossible triangle in Perth, which you can see here. Of course, you can only see it at a particular position because obviously it's impossible. But there it looks. There is the photo of his impossible triangle. And here is the Cosmology Gallery that we built up at Gingin as part of our Gravity Discovery Centre. And there are the tiles. But my other connection goes back 40 years before, because I was fascinated with his non-periodic tiling in the days that I used to be an amateur potter. And the top left of that slide shows some of the non-periodic tilings that I made. I was actually had a plan to put these tiles on my bathroom, but I never got round to it. But I found some of those tiles and took this photo just the other day. The Cosmology Gallery has a floor of the non-periodic tiling, but its roof is a platonic solid from 2,500 years ago. So in our Cosmology Gallery, which has a cosmic microwave background and all sorts of things in it, we have this beautiful contrast between ancient geometry and the modern geometry of Penrose's. But in looking this stuff up, I found a beautiful YouTube Veritasium YouTube talk, which has just been released by Derek Muller just this month, about non-periodic tilings and tilings in general. So I just want to commend that to people. It's a wonderful 20-minute YouTube presentation about these tilings. So let's go on to what I'm really talking about, which is the other two Nobel Prize winners. And the story starts in 1951 with two of Australia's pioneering radio astronomers, Jack Pittington and Harry Minette. These guys had been involved with radars in the Second World War, and they went on to become radio astronomers. And they found a source, and they said it lies close to the galactic plane and very close to the center of the galaxy. The significance may be considerable. So this was the first absolutely clear recognition that there was something very interesting at the center of the Milky Way. The story carries on about 20 years later as radio astronomy had progressed a long way. And I found a few quotes and a few quotes of some letters and things about this early work. Downes and Goss in 1972 said, "It's of paramount importance to pursue investigations of the compact structure in Sagittarius A. It is so close, we can observe details on a much finer linear scale than is possible in external galaxies. Because by this time, powerful radio galaxies have been found emitting jets, and these were the quasars that we now know are objects with huge black holes in the center and accreting matter onto the black holes. But in those days, they were still rather mysterious. And then it was very clear that there was quite a bit of competition for seeing these interesting parts in the sky. A letter I found, here are a few thoughts. Fred Lowe reanalyzed some of his 1973 observations. We better publish fast if we want to beat him into print. And then the next one is interesting too. Dave Rank and I are going to try to detect these sources in the infrared. I'll talk about why in a moment. Please keep the positions kind of quiet because Becklin and co can wipe us out if they want to. So people were competing to try to get better understanding of what was going on there in the center of the Milky Way. And the suggestion had made that they should be using radio. One of Australia's foremost radio astronomers then comes into the picture. This is Ron Eckers. I guess this is one of his early papers in 1975, a full synthesis map of Sagittarius A at 5 gigahertz. Notice the scale there, 1 parsec on that map that they came up with. You're still looking at a very big scale there. We're seeing something that's of order 10 parsecs across, 10 times the distance between here and Alpha Centauri, for example. But there is a very intense radio source right there. So it was starting to be pinned down. And by 1975, many astronomers were beginning to guess that the brightest, smallest source there was a black hole. And gravitational wave physicists had a special reason to hope it was a black hole, because that was the year I came back to Western Australia to start gravitational wave experiments, trying to build a gravitational wave detector. So I want to just tell you why we cared so much about black holes. And this goes back to the guys that Susan's been talking about, Schwarzschild and Einstein. Schwarzschild's solution that Einstein received in January 1916. And if you thought about something like the Earth becoming a black hole, it would have a Schwarzschild radius of 10 millimeters, and sounds absolutely crazy. But then the same year, a few months later, Einstein obtained an approximate solution for his equations, which was the equation for gravitational waves. 1918, he corrected it. A bit of help from Eddington, or Eddington was involved in the arguments, but I want to just focus on the formula he found, which is called the Quadrupole Formula, which is when you apply it to two stars orbiting each other, it says that the power output of two objects orbiting each other is given by a factor g over c to the fifth times the mass squared times the size to the fourth times the speed to the sixth power. Now, the key thing there is g over c to the fifth. That's an incredibly tiny number. So this number tells you that whatever system you have, the power output in gravitational waves is going to be pretty tiny. And so Einstein said that gravitational waves are of academic interest only. Remember, Einstein had this Schwarzschild solution, but he didn't really think it had much significance. But then jumping back to the 1960s and the 1970s, when there were started to be signs that there were black holes out there, people did something very, very simple. And what they did was just to re-express that equation that we just saw on the previous slide in terms of the parameters of black holes. Well, black holes have an escape velocity equal to the speed of light, meaning that if I have two black holes coalescing, they have a speed roughly, getting very close to the speed of light. And that occurs at the time when their size is of order of the Schwarzschild radius. And the power formula transforms in a sort of a seeming miraculous, but in fact, a pure algebraic way, into c to the fifth over g, an enormous number, times those two ratios that you can see there, which both will have a value of order 1. So suddenly we have transformed from something that is a source of gravitational waves, which is utterly negligible, to a source of gravitational waves, which has a power of order c to the fifth over g, which corresponds to 202,000 solar masses per second of pure gravitational energy in the form of gravitational waves. Tells you that black holes are the universe's most efficient converters of mass to energy. 5% of black hole mass converts to gravitational waves. So you have this strange sort of explosion predicted now, an explosion of pure gravitational energy rippling through space-time forever. And that will happen if black holes coalesce. So I think you can see why gravitational wave physicists love the idea of black holes, because binary black holes would be super powerful sources that even with inefficient detectors, we might be able to detect. So we really wanted black holes. We needed black holes. We wanted them to exist, and they sustained our hopes and optimism for 40 years as we struggled to build gravitational wave detectors that were sensitive enough to detect waves. And of course, that meant that we watched the galactic center studies very, very carefully. So that's the connection between the center of the galaxy, where there started to be better and better evidence of a black hole, and gravitational waves. So here are some of the later images looking at the center of the Milky Way. You see that incredibly bright in the left picture. You can see the incredibly bright source of radio. You can see various other things, including supernova remnants. And but look at the scale there. The scale bar on the left is showing 75 parsecs. This is a very big scale structure we're looking at. But as you look down into the center, you start to see structures created by magnetic fields, those lines or streaks of some magnetized gas, and that central source. But what we're interested in, and what our Nobel Prize winners were focusing on, was right in the center of that region. It's useful, and here again, we zoom in much closer, and the part of interest is obscured by lots and lots of gas, and it's shown on that slide there. So we have, in this region, visible light is attenuated to about 1 part in 10 to the 12th. But there is a tiny window, which was alluded to in that 1972 discussion, that in the infrared, and around about 2.2 microns wavelength, there's a chance to be able to see through the gas and dust, which is blocking this region from view. And the two teams, led by Reinhard Genzel at Berkeley and Munich, and Andrea Getz at UCLA, began a long-term study. The truth is that Genzel actually started this, and he, his mentor, Charles Townes, the Nobel Prize winner for the laser, was very much behind this too. So here's a picture of those two in the 1980s, when they were already starting to study this region of the Milky Way. Andrea Getz, I was at a conference in, I think, at 1995, when she said, this is not an exact quote because it's not in writing, but it's from her talk, the galactic center is too important to leave to one group alone. She made a decision to go in and try to validate the work that was being done, to try to understand exactly what was happening by setting up a second group at UCLA. She brought improved imaging using adaptive optics on the Keck telescope, and she's the fourth woman to win the Nobel Prize in physics. So these are the two people, and it's really important to emphasize the incredible difficulty of seeing these highly obscured objects in the center of the Milky Way, and it needed the biggest telescopes in the world and the most fantastic astronomy. But what's the physics of what they were doing? It's very, very simple, and it's simply the physics of orbits, Keplerian or not exactly Keplerian, because this is general relativity, but orbit speed tells you the mass of the central object. From 1970s to 1990s, people were looking at the orbital motion of different material, looking at the Doppler shifts in spectral lines for gases, but they were not getting very good resolution. But it already implied, by looking at material somewhat near to the center of the Milky Way, that there was a central mass present of millions of suns. But initially, it could have been just a dense cluster of stars that would have been able to explain the observations. It didn't require there to be a black hole there, but there was a central cusp in the mass distribution, but not necessarily a black hole. But better and better resolution slowly ruled out anything but a black hole. But the other thing you can do with by measuring orbits is probe the environment outside the orbit as well as within the orbit, in the same way that the planet Neptune was recognized that it must exist because of the perturbations to the orbits of Jupiter and Saturn. So we can say something about what's outside as well as what's inside. Here's a video showing the a zoom in towards the region of interest. Zooming into the Milky Way, you can see the black dust, which makes it extremely hard to see this part of the Milky Way. We're zooming in 24,000 light years. Here we are at near to the center. And here you can see the stars are moving. But now I want to show some of the original videos that were created. And these are videos showing the years from 1990s to 2018. And you can clearly see stars moving, but you can also see the difficulty of this imaging. The stars appear brighter and less bright. I'll just play it one more time to let you see the interesting part in the center, and this particular bright star, which we can see is moving in an elliptical pattern with an orbit of the order of 8 or 10 years. But it's nicer if you can clean these things up. I want you to also notice the scale bar there, 0.1 of an arc second. So this requires incredibly good angular resolution, and that's not possible without using adaptive optics to take out the scintillation and so refractive errors from light passing through the turbulent atmosphere. So here's a cleaned up picture of orbits, and we can see partial orbits and the same complete orbit that we saw in the first one, and some extraordinary orbits like the one at the in the diagonal top left, which is highly eccentric. And you can then extrapolate some of these orbits into the future to say how we might see this if we look further. There's the same movie again, but now we're going to see the completed orbits and and what is very, very clear is that there is one single central object, and some of these stars are going very, very close to that central object. And it's that close proximity that is telling us that that has to be a black hole, that there is no other type of source that would be possible. So let's just look at some of the numbers for this galactic center black hole. The black hole mass is around about 4 million suns. The total mass of stuff within 3 light years is about 1 million suns. So there's about a million solar masses of objects, which can include black holes and white dwarfs and planets and all sorts of things in within 3 light years. So that's that's within a distance less than the distance from here to the nearest star, we have a million objects. So it is vastly denser environment than anything we see around here. The size of the black hole is 24 million kilometers. And the number of stars measured that feel the black hole's influence and that's orbits are affected is in the order of thousands. So those videos are giving a rather simplified view where you're only seeing the best and the brightest. The fastest star is infalling at 8% of the speed of light, 24,000 kilometers per second. Compare that with the sun, which is going at a few hundred kilometers per second in its orbit, and the Earth, which is going at 30 kilometers per second. These stars are going at incredibly high speed. The closest approach to a black hole is 1900 million kilometers, which is in the solar system represents a distance just beyond Saturn. So these things are going pretty close to this black hole, which has a size substantially larger than the sun, approaching maybe halfway to Mercury's orbit. They are really getting close to the black hole. But I want to then just connect this back to gravitational waves, as Susan did, because since 2015, as Susan mentioned, we've been hearing black holes colliding in gravitational waves, just like we had hoped. The black holes are bigger than we had expected because these 30 or so solar mass black holes are larger than any inferred black holes that have already been found in the solar system, in the Milky Way, which is more like around about 10 solar masses. It's important to understand that from the gravitational wave sounds, and when I say sounds, I mean how the frequency, which we hear actually in the audio frequency band, frequencies around a few hundred hertz, how the frequency changes with time tells us precisely the masses and the distances and roughly where they come from. General relativity allows us to probe really deeply into these systems. And here's one of our latest in a video narrated by Mark Myers of OzGrav.
In May 2019, LIGO discovered the most massive black hole merger ever observed. Two monster black holes collided to form an even more massive object, about 150 times as heavy as the Sun. Not only was this the first time an intermediate mass black hole had ever been directly observed, but one of the monster black holes that created it shouldn't even exist, according to standard theories of how stars die. At the end of their lives, stars of the mass over 10 times larger than our Sun explode in a supernova and leave behind a black hole. But stars with a core mass over 65 times the Sun destroy themselves completely, leaving nothing behind. However, stars with a core mass over 135 solar masses avoid this total destruction, collapsing directly into a black hole. So black holes between 65 and 135 solar masses should not exist. There are two leading ideas how it formed. Maybe it was made of smaller black holes which merged together, building up progressively larger black holes. This could happen in a dense environment like the center of a galaxy or a globular cluster. Or perhaps a star late in its life collided and merged with another star, making it big enough to form a massive black hole whilst avoiding total destruction. The resulting intermediate mass black hole is the missing link between the two known populations of black holes. Stellar mass black holes with masses up to about 60 solar masses, and the supermassive black holes that exist in the centers of all galaxies.
And then on the last topic that Mark just mentioned, which is the supermassive black holes. In 2019, the Event Horizon Telescope managed to image the black hole at the center of M87 galaxy. That's 6.5 billion solar masses, 40 billion kilometers diameter. So this is a monster thing, and the first time we've been able to actually see a black hole. So this Nobel Prize is part of a bigger picture of understanding black holes, as we can see. And in conclusion, we've got mathematical proof that black holes must exist in Einstein's theory of gravity from Roger Penrose. We've direct evidence of their existence from listening to gravitational waves when they coalesce. We've imaged them with the Event Horizon Telescope, which perhaps is maybe the next Nobel Prize. The Milky Way black holes has stars swarming around it and 1 million suns worth of other stuff. And from all the black holes observed in gravitational waves, we can predict that large black holes are coalescing about once every 5 minutes in the visible universe. Maybe what's most interesting are the questions, so the things that we don't know. We don't know how many black holes there are out there, especially single black holes, nor do we know how they formed. It's still quite uncertain. And theoretically, why must the universe have black holes? I can't answer either of those questions, and maybe this will take a long time and more Nobel Prizes to get the answers. Thanks very much.
Thank you very much, David, and thank you very much to Susan as well. I'm cognizant of the fact that we are running over time, but maybe, David, if you could just answer one question. We have a question saying, what happens when a gravitational wave hits a black hole?
Really good question. Gravitational waves, just like anything else, will be absorbed by the black hole, and as they pass through, the black hole will increase its mass.
Okay, excellent. Well, I think that's all we have time for. Thank you to all our participants, our organisers, and most of all our speakers today. Very much appreciated, and we're looking forward to further black holes in this, further Nobel Prizes in this fascinating area of physics. Bye-bye, everybody.